I want to get started now. I have these little devices, which is kind of scary. It can make some noises, so I hope you can bear with me if it suddenly speaks up. I think it meant to amplify my voice through the speakerphone, but I'll try to be less interruptive in here. Okay, so let's get started. Any questions from last lectures? Maybe one question I got is that why in the cover page we got two logos, CMU and Petron. Okay, I take 30 seconds to explain that because right now I'm jointly affiliated with CMU as a professor. I'm also the founder and the chairman of company Petron, which I founded 3 years ago. So I'm still working in the company, and that's why I wear two hats. And these two projects are very, very interrelated because what I'm teaching here got built actually also over there, in terms of the products, in terms of the solutions. Okay? And of course, in the future, if you look for projects and internships and other things, feel free to contact us. All right, so lecture 2, we're going to now move on to unstructured, undirected graphical models. So last time, we talked about conditional independencies, correlations, and so forth between two random variables. And we come up with a few tests to determine whether two random variables appear, are dependent, correlated, and so forth. Right? So we basically were asking, is this true or not? And based on that, we can draw a node or draw an edge. Right? And then we also went on and say, well, after all, in the real world, you have more than two random variables to worry about. You are operating in a multivariate environment. Therefore, at least I need to care about X and Y, given a bunch of others. Right? So what technique we use to test that kind of independencies? Quiz 1. Do you still remember some keywords? What's the correlation how to measure a correlation between two random variables given a bunch of other things with linear effects? I'm going to make it very, very limited. What's that? Pearson correlation. I'm asking the next level question, which is given some other bunch of things. Yes? Partial correlations, right? You measure the residual, of the two random variables, subtracting the other things using Pearson correlation. And then we say that partial correlation or correlation isn't necessarily translates to independencies. You can use mutual information to measure a pair of pairwise independencies, but in terms of the correspondent of partial correlations to other things, it becomes a little more complicated. And we say a bunch of other conditions like under Gaussian, under linear effects, you can really build equivalence between partial correlations and independence and so forth. Right? You can go back and carefully read those notes and hopefully get yourself cleared. But nevertheless, all we learned last time was not necessarily leading you a graph, or maybe it is a very, very tedious way to get you a graph because it basically only worries about a pair. Imagine you have a graph with a few thousand nodes. You literally need to look at every possible pair, given every possible combinations of other things, which is a power set. You run into an NP-hard problem. Therefore, building a graph like that based on all possible dependencies or independencies is not quite feasible. Okay, so today we're going to go the other way around. We're going to say, I'm going to draw some graph, and let's at least tease out, read off all the dependencies, out of there. And then I may say that, can I establish some kind of equivalence that establish between, the kind of top-down approach where I just write a graph and build a model versus I started from a whole bunch of independencies and go reverse and generate or create that kind of models. Okay, and if there is a good equivalence, then you can imagine that you have a simple kind of life now. You can really rely on a graph-guided kind of construction of the distribution rather than the bottom-up test and disprove and so forth. Okay, so that's the plan for today. I want to, again, it is very notoriously known that notation becomes a big issue in our area, in statistics and also in machine learning. All authors like to use their own notation. And in fact, even in a single paper written by a single author, the notation can change from page to page. That's, I also have that kind of problems from time to time. So at least let's get some basic notational agreements. Okay, we're going to use capital, character and lowercase to indicate random variables. Okay, and typically, these are, if are non-bold faced. If sometimes, you see I don't know even how to write it. So a bold-faced expression in print, that usually means that this random variable is observed. It associates with a value. But again, sometimes people use a matrix, call this a matrix. But anyway, you at least know that we have variables and its values. And index basically means that the ith variable, in case you have multiple random variables. And if you have a soup index, that means this particular variable has many dimensions. And that basically gives you the index of every dimension, sorry. Okay. Random variable basically is a variable that is associated with a distribution of its values. Okay, it's stochastic. And random vectors, are often also expressed as this. And sometimes, for clarity, people put a vector on top of it. Okay, but without further clarification, sometimes we just interchangeably use these also as an expression of random vectors when it is self-explanatory. Random matrix, yes, it is again that bold-faced thing, meaning that you have stacking array of multiple vectors. Parameters. Okay, we're going to deal with parameters very often. We use instead not Roman characters, but the Greek characters, alpha, beta, or in their capital form, say theta like this or this. Okay, so that's roughly our notation. You will see more when we actually get into the deeper presentations. Now, undirected graphic models. So here you see a graph which has a number of bubbles, nodes, and a number of lines, which are the edges connecting a pair of nodes. And there are no errors on the lines, therefore it is undirected. Okay? And undirected graphic model is this. It is a probabilistic distribution over this set of random variables whose parameters are actually defined by G, the graph. Okay? And you will see why I say it that way. What does it mean by defined by G? And from the graph, you can already read off some pairwise relationships. I wouldn't say correlation. Some relationships is there. It is non-causal because there are no directionality. And in the future, you will see that you can use this technique just to write down arbitrary models of that kind of nature. Whenever you see a pairwise relationship, you could graphically express that. With the kind of the description or definition of the model, this model is defining a distribution of the joint value assignments, but you cannot use this model very easily to sample or to generate examples of instances from this distribution, and we will see why that's the case down the road. So what is the meaning, specific meaning between of these edges, and what's the impact they have, on the node configurations? That's the topic for today. Let's first look at a few models of this kind, so that we can start to appreciate, what kind of impacts or values we can obtain from such model family. Okay. Let's take a real problem. So here is a real problem. I want you to work on a computer vision problem, which is just to classify every pixel. Okay, literally classify every pixel in the image. This is the foundation of object recognition, segmentation, and many computer vision projects or problems. In fact, maybe not classifying every pixel, but every patch of pixels. Okay, so here is a patch. And I made the problem very simple to make it a binary. It's either air or water. I want you to classify now. So let me do a poll here. Those who believe this patch is the air, please raise your hand. Okay, that's roughly a quarter of the people. How about the water? Raise your hand. Wow, why? 3/4. Amazing. I actually don't know yet. I haven't seen the bigger picture yet. Okay, so we have a 1, 2, 3 breakdown roughly of this. Okay, so let me do one more thing. How about I do this? Oh, okay. Did you see this lecture before? 1/3, no, 3/4 of you are getting things right. I was surprised. In fact, I didn't know. So looks like this patch corresponds to the area over there. Why you believe it is water now? Or do you think it makes easier, when you see this picture? Well, it is on the top of the image, which makes it more likely to be air, right? But it is also next to the land. And as you'll see, even beaches and so forth, right? So that probably gives you some clue. So what those kind of common sense reasoning entail, in your formal reasoning, right? And how do we describe those mathematically so that when two people or when a computer look at this model or this image using the model, they will draw the same conclusion? So that's our question. So a modern technique is to divide this whole thing into a grid, and on every patch resulting from this grid, you define a random variable to indicate its binary classification value. And what I said, for example, on top of the image or next to some other entities is a concept of adjacency and continuity and so forth, right? So when you say adjacency, continuity, you are talking about more than one random variable already, maybe at least a pair, right? That's why, in this grid we have nodes connected by an edge, either directionally or undirectionally, doesn't matter. And then you can put some contingency table, over the joint configuration of these two random variables, say x1 and x2. You can basically put a joint configuration, say they are both 1 or 0, or they are 1 versus 0. You put a number there. It could be a probabilistic number. It could be any number. You could even put negative numbers there. Say, two adjacent nodes are likely to be labeled the same. That's probably closer to our common sense. And then you can encourage this and that with a better number, right? And if they become opposite, well, you put some other number and showing your belief. So that is a model. Okay, it is literally a mathematical model, and that's the model you saw in our previous lecture as an example. It is the grid model. Every single pixel basically, all in other words, say atoms or gold games and so forth, they can represent a configuration. So this model actually, gets invented very naturally from image processing and the lattice physics and so forth. Okay. And in physics, particularly, that is intuitive to a physicist because, here, if you imagine everyone is an atom, we know that, magnetics, the Fermi anti-parallel and the parallel spin of the electrons, right, in those little atoms. And how to describe that? Well, usually the same orientation of the spin will repel each other, and otherwise they will attract to each other. So this kind of knowledge gets expressed using this model as well. We have a few other examples. Social network, you saw it. Protein interaction networks, you also saw, you didn't see it, but it's very popular in computational biology. Again, they kind of models a kind of a mutually symmetric relationship between proteins. We saw it. In fact, even in other fancier domains, such as information retrieval, you can use this model to describe, a relationship between concepts and also, entities. For example, here, this model was invented to model the correlations or alignments between images and texts, and how they are aligned. Well, there are some hidden topics which gave rise to, or which correspond to certain words or certain image, configurations, in the data, and that leads you to, another type of a graphical model. We will actually revisit this model very shortly after some technical presentation. Okay, now I think we saw a few models. Let's get down to a formal representation of the model. So we define a graphical undirected graph model to be the following. Okay, given a graph, you first, can identify all the cliques on the graphical model or on the graph. So here are a few cliques. For example, this is a clique, right? And do you see other cliques? An edge connecting two nodes is a clique, right? So anyway, we are going to define clique in the next page, but say given cliques already, we can define something called a potential functions on top of this clique. What is a potential function? You will see actually very, very soon. It's a positive, function, on configurations of discrete or continuous random variables. They need to be positive because if you have a negative number here, when they are multiplied, they will produce a negative probability, which is invalid, right? And also by this product, is basically the multiplication of the potential function defined on all cliques over a particular configuration. Okay, how to make them to be a probability? You need to normalize it, right? Because what's the basic property of a probability? They have to be between 0 and 1. They have to be positive. It has to be also between 0 and 1. And also all probabilities of all possible configurations over the same set of random variables has to sum to 1. Right? Therefore, when you define what is known as the partition function, which is forcing what I just claimed to be true. Okay? You just literally, you can see this is a huge sum over all possible configurations of all random variables that you care about, in this case, 5 of them. And it is a sum because it is discrete. You can enumerate all configurations. If it is not, then you need to have a nested chain of integrations. But this number is actually very, very important to make this a whole thing hold together to be a probabilistic distribution. Okay, I'm not going to say too much yet how to compute Z. It is an extremely, extremely difficult task, which actually inspired a whole area of research in nowadays called variational inferences. But these models are known as the undirected graph model. It's also called Markov random fields, Markov networks, and so forth. And before I move on to the details, I want to close by saying here that this potential function is what gives you the power. Okay, it gives you an ability to specify some contingency functions that offers bias of one configuration over others. Okay, so if you want to design a model, you actually have now a legitimate vehicle to inject your human knowledge. And later on, we're going to also discuss how to learn model from data. Then these are the placeholders, okay, to extract numbers out of the data so that they reflect the bias, in the data. But they are pre-probabilistic. Okay, we could make it probabilistic, but it's very difficult. Sometimes you just say, I want this configuration to be score 10 and another configuration to be score 0 or score 1. It's more intuitive for human to specify, okay, rather than I need to divide out numbers, make sure that everything sum to 0 or sum to 1 and so forth. That's why, the potential functions are the pre-probabilistic scores, not probability itself. In fact, it is impossible to make it a probability itself. I will give you a few counterexamples in a second. Okay, so take a closer look of the cliques. I suppose you all know what it is already, so I'm not going to say too much. Here, the most important concepts, one is called the max clique. So clique basically is a set of nodes which are all interconnected, right? And the removal of any one edge will make some of them disconnected to other nodes. Max clique is where it's a complete graph where if you max clique is basically a clique within a graph, in the sense that you add any additional nodes on top of this clique from the graph, you don't see clique anymore. Okay, so that's called max clique. Then subclique is something that is within the max clique. Okay, so here are some examples. You can clearly see that we have 2 cliques here, and then we have a few subcliques. Okay, so why we care about clique? In a graph, why we just not start from the nodes and edges like what we did in the early class, but now we kind of rise ourselves to the clique as a unit. Well, in the future, you will realize, graphical models, at least from the orthodoxical kind of a probabilistic standpoint, is used to model dependencies and independence and so forth. So within a clique, because they are all interconnected, you need to have a design or a model that allows all dependencies to be allowed. Right? So you'd better build your foundation from that point, because if you build from the subcomponents within a clique and then make them to assemble a clique, you may risk losing some of the dependencies that is not obvious from the subparts. But if you start from the clique, at least you can make sure that you don't miss anything, okay, within that clique. That's kind of a very higher level statement. Okay. And then, when you go beyond clique and above, well, that's fine. At least that building block is all rich enough to capture everything. And then you can start to make assemblage based on the graphical model laws that I said earlier, like this multiplication law. Okay. And that basically leads to the natural definition of distribution. I just flash here again. This distribution was also known as the Gibbs distribution. Okay, and these are called the potential functions, clique potentials. So let's just say a few more words about what this clique potential means. I said earlier, they are pre-probabilistic. They are contingency functions giving you a chance to recover or specify biases on configurations over others. But why they have to be pre-probabilistic? Just use an example. We have a very simple graphic model in here, which has 3 random variables. And let's write down a joint distribution symbolically. Okay, we're not going to put any analytic form on that. And you can basically use a chain rule to factorize it. You can factorize it in many different ways, and here is one way. Okay? And if you look at these three components, and you want to identify those units that contain two random variables at a time, I guess you have maybe two ways of doing that. One is to kind of group together the first two elements and save the next one, or the other way around, make the first one a standing alone and the next one to be. You can see, even I start from a joint probability and factor them into conditionals or marginals. When I use the potential language to define the entity, which potential is defined on cliques, you will see that these two potentials carry different probabilistic meaning already, right? One potential is a marginal or a joint of x and y, and the other is a conditional of z given y. Or if you switch, with another factorization or maybe a combination, then you get the first potential to be a conditional and the second potential to be a joint. You can basically not claim that a potential is either a joint or a conditional, okay, or marginal, right? So that basically already implies you the difficulty of, attributing a single universal probabilistic definition for the potential function, and therefore people just forget about it. Let's forget about the probabilistic interpretations of the potential. Let's just go even beyond conditional and marginal. Just go any positive numbers. Okay, goodness of compatibility, happiness between two people, you name it. Everything that you feel appropriate to describe two entities can be used here. Okay, so let's go down and see a few more examples. So here, you can graphically see what is a max clique, and then what is the potential on the max clique. Well, potential function here is symbolic, but if you really want to implement it in a computer, here you have three random variables. Therefore, you need to use a cube, which is a three-dimensional table, to put numbers for every possible configurations. So that's a clique function. Okay, and therefore, your joint distribution is basically defined by the product of two potential functions defined on the max clique. Of course, computing these requires you to sum over all the four configuration of the four random variables. You don't have to only stick with the max clique. You could also do this. You can just use the subcliques. Okay. And then you have a different way of specifying. You will lose something, in fact. It is possible that there are some tricky configurations in the triplets that is not necessarily recoverable, or at least recoverable easily from the pairwise potentials. Okay, but this is at least another way of parameterizing the model. And there is also another kind of canonical representation, which allows you to be overcomplete, which means that why not defining the joint distribution from all potentials existent or all cliques existent in the graph, which includes the triplet cliques, the pairwise cliques, and also the singleton cliques. Okay, every individual could also have that gives you the ultimate flexibility. In a sense, you could have placeholders to numerically capture all kind of tendencies and affinities and everything between pairs and triplets and the singletons. Okay, and of course, computing the potential function becomes a little bit more complicated. And this one is the most expensive and also the richest form, which actually subsume the previous two as as special cases. When you, of course, implement your own model, you, of course, need to trade off whether you want to consume a lot of memory to build a full model, or you want to be a little bit more frugal for the exchange of efficiency. Okay, so that's the structure part. okay, and the representation part. The second part is what do you read from the graph or from the model in terms of independence properties? That's basically the question we asked in the first lecture. I want to start with a few definitions. In many cases, the way to define a distribution can be as explicit as just in terms of the set of independencies between variables. Okay. Therefore, we need to first define a family or a placeholder for those dependency properties or statements. Okay. So let's begin with the first definition, called the global Markov properties of undirected graphical model, which is like this. I stands for the set of independencies. I of H is basically the set of independencies on the graph H. And this is a set which is defined as the following. It defines, it includes all the pairwise independencies given the third party. Okay, in the following sense, we claim that X is independent of Z given Y. By the way, X, Y, Z now are generalized from a single random variable to variable sets, okay, which includes single random variable. They are conditionally independent if they are graphically separated, okay, in the H graph. That is known as the global Markov property. There is an analytical way of proving that, which is very trivial. So I'm not going to show that. I may show that in our next lecture for graphical models, which is even more trivial. Therefore, it's easier for me to prove. Okay. But the idea is the same. So graphical model in the undirect sense give you this automatic property already. You can safely extract conditional independencies between two sets given the third one if they demonstrate this graphical property, that they are graphically separated in this way. Okay. Therefore, given a graph, you can obtain a set, by running this macro over all triplets. Now comes to the definition of IMAP, because we want to now establish the relationship between, a graph and a distribution, using the conditional independence definitions. So let's begin by a distribution, arbitrary distribution P over X, and we define this I's of P to be the set of all independencies, all independence assertions, of the form this that are held in P. Okay, and we don't need to know the parameter value. Basically, we assume that as long as the graph is there, whatever way you parameterize or put numbers into those contingency table or into this potential, they should all honor these independencies. Okay, so we define P to be that set. And then let's define K. And by the way, this one right now isn't touching upon the concept of a graph yet. Okay, basically it's almost like a symbolic and analytical, which is that give a P, imagine that you can always run proper conditional independence tests to extract all these. How to do that? Well, it is really about does X, Y, Z honors P of X you basically can imagine you can try all numbers in your distribution, and as long as they satisfy this equivalence, then this independence is established, right? And you can basically imagine a set can be built like this, which is very difficult, by the way. No one actually want to do it unless you have only 2 or 3 random variables, right? Then I have a graphical parallel exercise, which says that I have a K on which you can read off the independencies using the Markov property like this, right? Which is way easier than building the test like this. Okay, and you can also come up with a set of independencies K. Okay, And what is the relationship between K and P? Okay, so we first define that the concept of IMAP. We say that if the independent set over K is a subset of any other given I set I, then K is an IMAP of I. Okay, and then what is I? How about let's call I, IP, which is the imaginary set of independencies coming from a distribution. Okay, then if this graph K, defines a IK that is a subset of IP, then we establish a relationship between a graph and a distribution. Okay, K is the IMAP of P. Okay, this is a little bit more formal, how to establish a graph, versus a distribution. Okay, clear? Pure definition, no need to prove. We just determine to call them that way. And that's making your life sometimes easier without looking at the numbers. Okay. Why? Because, for example, let's give an example here. I used to have a table, but let me just write it. Let's imagine a two variable distribution, which let's say no. I hope I'm doing correct. Am I? Okay. So this whole thing adds up to 1. So here I define you a distribution. Okay. And now looking at this, I ask you to say something about the joint distribution P of X and Y. What can you say?
What is the last column?
What's that? Oh, the last column is the P. This is the configuration. Remember, we always use a truth table, a contingency table, or probability table to specify discrete distributions. And see, here is an instance of your simplest two variable distributions. Now I give you these purely numbers. In fact, you can see that it took me a while to even come up with these numbers just now. I have my way. I have a little macro here to come up with those numbers. Now I just give you this number. What can you say about this joint distribution? It is a joint of P, X, and Y. I'll give it a try. I put all these numbers very painfully here to make my life a little bit easier because they have some very interesting properties. Yes.
X and Y are independent.
Okay. Good guess. Why?
The total probabilities is like the sum of the probability that X is 1 is 0.8.
Uh-huh.
The probability that X is 0 is 0.2, and the same thing for Y.
Yes. So you are saying that actually this particular way of defining the joint allows me to write this into a product of P of X and Y.
I think so.
And then this P of X actually is a 0.8.2, and this is also a 0.8.2 breakdown, right? All right. See, you look at the numbers very carefully, you actually discover something very, very intricate. They are independent. If I change the number to be 0.65 and everything become other, then maybe I will just stay with everything the same, and I augment this to be. It's very close to this one, but then you fail to discover any independencies. I can do that legitimately, right? So that's the pain of a numerically expressed graphical model or probabilistic model. These are just two random variables. If I give you 10, I bet you cannot really discover any independencies, right? But if I say, hey, I have a graphical model where I have this. Or I have another graph model which I have this. And then I define distributions. I say the distribution is defined on that and that by putting any numbers by the way. Because here I used to have 6.64 and 0.16, but I could also put in other number which still make them factorizable. Then you need to do another calculation, right? But in here, if I already tell you that my model was built using the previous definition of potential function multiplication and using this graph, then you already know that it is guaranteed to be independent. Right? So that's basically, giving you hopefully a hope, maybe an interest on, or maybe a conviction on why, working with graph is more convenient than working with numbers. Okay, but I need to establish some good equivalences between the graph. For example, the graph shouldn't mislead you. It shouldn't be that I actually claim to have a independence in the graph, but actually in my distribution, they are dependent. Even though I follow the rule of building graphical models as I just specified earlier, which actually has a name called the Hammersley-Clifford theorem. So how to establish this equivalence? Okay, so let's go back to our main track and further study the independencies. So this is the definition of Markov for independencies, which builds on graph separation. And then all triplets satisfying graph separation, defines the set of a global Markov property on H. Here we don't say, you can see it's purely on H. There isn't a probability yet. Okay. And also there are other forms of independencies, such as this one known as local independencies. Okay. It's actually very easy to appreciate because there's another name for it. It's called, what is that? The Markov blanket. For any random variable, or any, maybe we stay away from saying random variable because right now we're talking purely about graph, not distribution yet. For any node or vertices in the graph, we can define its direct neighbors, okay, which are connected to this node by an edge. And then local Markov independence says that the node of interest is independent of everything other than the neighbors and also the node itself, basically all this white stuff, given the Markov blanket. Okay, so it's very intuitive. This red guys is like a blanket, isolating a particular node in the middle away from the rest. And they actually characterize a local Markov independencies. Okay, so you can come up with this set, run over every node or every set of node, and draw its Markov blanket, and you have a pure, more set of, independence properties.
I think in a different class I had seen a definition of Markov blankets that included coparents.
This is an undirected graph.
Okay.
Therefore, you will see coparents in our next lecture. Yeah, I'm coming with a simpler sequence now. I used to talk about coparents first and then get people confused. All right. So now we worry about the sumness and completeness. Now we need to connect the graph with the distribution. We say that H is an IMAP of a distribution if I of H is a subset of IP. Okay. And the good news is that if we define the distribution using this formula called the Gibbs distribution, we just saw before, which builds on the product of all potential functions defined on cliques. Okay, they are not arbitrary potential functions. They are potential functions only on cliques. And normalize it properly. Then you have this so-called soundness guarantee, which is that you are guaranteed that H is an IMAP of P. It's a nice guarantee. At least you are not going to get more independencies that is not in H honored A in P. Okay, so this is soundness. That basically allows you to now go from H to a distribution very easily without putting up all the tests on H to extract or to encode independencies. The independencies come as a first citizen from the graph and then gets honored through this equation in the distribution. Okay, so remember this verb. Actually, we have a scriber today, right? So this is very important. The independent set from a graph is the first citizen, and then they use this Gibbs distribution as a vehicle to induce a distribution, and then gets all the independence in H honored. Okay? The reverse is a little bit tricky. Okay? It means that if I have a H, all the independence and so forth encoded in H. Okay, maybe that's basically the reverse way. It's a little bit trickier. I'm going to do some more proof in our next lecture together with the direct graph model. But here is just a statement of what you are going to come up with, to live with. It's almost reversible, but except a few cases. For example, here is a statement of the completeness theory, which says that if the triplets are not satisfying a graph separation property, or it's not satisfying global Markov property, which suggests that they are independent. Okay, then if they are not in this, which suggests that they should be dependent, right? Because this set is the set of all independencies on H, and we are talking about a few triplets which are not in these sets. So you should believe that they are dependent. They are not independent. Okay, but there you can construct a few graphs which still makes them independent. Okay, so this is almost like a leaky theory. You expect that if they're not here, then they shouldn't be here. But they could be constructed in a way that they're here. Why? Well, it is because remember our previous way of specifying the contingency table of everything, right? I put them adjoint, and the joint of two random variables, but I can come up with some tricky numbers, which still makes the two variable independent under that particular number configuration. If I change the number a little bit, they become dependent again. Yeah. Therefore, it's not holding true for arbitrary configuration or assignments or of the probabilistic number, but you can always engineer a counterexample to break those dependencies or independencies. Okay, you can basically manufacture independencies just by playing with numbers. You can also play tricks by making a particular random variable with probability 0 on certain variables, regardless of anything. That's also possible, just by building the table that way. But again, these are very unnatural cases. Okay, typically, in the normal way of building, a probabilistic distribution from potentials or from other building blocks, you don't run into this. So the reverse is always almost true. Yes.
Why do you think that it's always possible to find such a thing?
Yeah, it is. Yeah, but still, it's some. It's the bigger infinity versus the small infinity. Okay, do you understand? Right? Yeah, you can always come up with these numbers, but unless you really are picking numbers, once you shoot a random dart somewhere, chances for hitting those numbers are very, very small. Do you get what I'm saying? Yeah. So I'm not saying this is, again, in the future when you're doing practice, typically these things are not even useful for you, but just conceptually you want to know that there are no strict equivalence between the graph and the P. And there are some other Markov properties which I just want to, fly by. You can go with yourself. What I just described as local and global Markov properties are defined intentionally to be very general, to focus on arbitrary sets. Okay, but for convenience, you can always reduce them to any pairwise independencies given other things. So these are another type of pairwise Markov independencies. Yeah. So I'm offering you basically a few ways of reading off the independencies from a graph on which a distribution can be defined. So in a sense, if a probabilistic distribution is constructed from a graphical model approach using the Gibbs sampling formula, then you can use all these rules to extract independencies. Okay. All right, and then let's conclude, with a theorem. This is called the Hammerschlag-Clifford theorem, which says that, there is this uniqueness of why we like this form, because, if H is a IMAP of the distribution, then P has to be a distribution, or a Gibbs distribution of H. Okay, that's the only way you should specify that. Okay. If you don't use this way, you choose to specify P otherwise, say for example, filling in a huge contingency table with arbitrary numbers, you are not going to make H a IMAP of that. Okay? But who will be doing that? The whole point of having an H is to basically utilize all these cliques to build it anyway. Therefore, chances for you to go against this theory is very, very small. All right. Lastly, I'm going to touch upon this in next lecture, called perfect map. There are sometimes a case where the H and the P become totally equivalent. Okay, that actually only happens for a small subset of distributions or graphs, and we will see examples of that. Okay, so then another practical concern that we want to mention briefly, which is known as the exponential form. As I said, potential functions over clique requires you to provide only positive numbers over joint configurations. Right? This is fine, from a numerical, mechanical design standpoint, but it is not very, very convenient for practitioners who work with real world, especially say physicists. You have the atomic electronic spin orientations, positive and negative. Why call positive 10 and negative 5? Right? Why not 8 and 4, or why not 10 and 1? There are debates. The most natural way is to call 1 plus 1, the other one negative 1. Right? So this kind of flexibility is very useful, in many modeling world. So therefore, you need to allow negative numbers, and that beats basically its validity for being a probabilistic component. Therefore, we exponentiate it. Okay, so we can basically redefine the potential function to be the exponential of the negative of the little thing called energy function. The energy can be positive and negative, it doesn't matter. Once it's exponentiated, it gives you a positive number. Okay, so that changed the form of the Gibbs distribution to be like this. Okay, it is the sum of the exponential of the sum of the little energies, clique energies. Okay, and this sum is known as the free energy. Okay, you can see it's getting very closer to the physics literature. Indeed, it was invented by a physicist. It's called the Boltzmann distribution. Okay. In statistics, it's called log linear models. Okay, because you take a logarithm on both sides, it becomes a linear combination of all the potentials. Okay, so now let's take an example. Here is an example of the Boltzmann machine. And let's let the random variable to be taking value from this space, only positive and minus 1. If you want it to be continuous, then it could be taking a range between some random variables. But in here, if it's discrete, people usually use plus 1, minus 1, or 0 and 1. And then we are going to define the potential only on pairwise potentials and the singleton potentials. In fact, all pairwise relationship between random variables. Okay, therefore you are going to sum over all the pairs. Okay, and this is called the Boltzmann distribution. And you could arrange the form to be a little bit cleaner by converting them into this linear algebraic expression. Okay, here you have a vector of x, vector like this, minus a mu u. Okay, and theta is the matrix of little thetas. Okay, so you have literally this matrix. Okay, and when you do the algebra, you will see that the bottom line is equivalent to this expression. Okay. Okay, so this is Boltzmann distribution, and why it is interesting? Well, in the future, I'm going to cover some techniques which allow you to learn this model to recover the structure of the graph from the data. So here we are always saying that we come with the model, the graph first, and write a distribution. And sometimes you actually want to understand the structure among random variables given a data set. It's very difficult for arbitrary cases, but this is one of the models which allow you to actually go backward and recover the graph. And in particular, the graph becomes interesting if this theta is sparse, in the sense that some of the entries are zero. What does a zero entry mean here to the graph? Are you still with me? These are the potential functions, right, over the clique, in this case over the edge. And they are basically the weights of the edge, right? Again, potential can be defined in many different ways. Here, I just choose the potential very simple to be their weights. Okay. If the weight is zero, that means this edge is not present. And usually, when a graph has a lot of edge missing, it becomes interesting, because otherwise you really don't have any knowledge. You say, oh yeah, this universe has everything connected. Well, then you cannot say too much. But if it shows some structure, then you can say that yeah, there are certain preferential attachments, certain causality or dependencies, and so forth. Right. So that's why biologists in particular, social scientists also, are very interested in recovering this kind of graph among people, among molecules, to understand their chemistry or their biology. All right, so this is Ising model. Okay, so this is called the Boltzmann distribution or Boltzmann machine. Ising model, we saw earlier for the image modeling, is a special case of the Boltzmann machine, which exactly reflects what I just said. Some edges are missing now. Okay, the only edges which are left is this, four-directional north, south, east, and west neighbors of every random variable. Okay, it's a grid. So this becomes interesting because that's how people understand, say, a certain atomic structure in the metal, or maybe in the image. So this is called the Ising model after the physicist Is. And then there is also a model called the Potts model, again named after a physicist named Potts. And in this model, the only difference is that x is no longer a binary node of -1 and +1. They can be a finite set of different states. Okay, maybe 1 all the way to C states. And why this is interesting? Well, if you have a RGB picture, you want to model the color, right? You need to have 3 kind of configurations. And if you want to model sentence or characters, do spelling checking and so forth, you have 26 characters and so forth. Right? So that's where more complex model become relevant. Okay, now hopefully we have enough materials and vocabulary to understand a slightly non-trivial model, which has a very, very important historical value, which is known as the restricted Boltzmann machine, RBM. Okay. RBM is the father, the root of now very popular deep neural networks. Okay. In fact, the solution to RBMs by Hinton's and his colleagues and among many others, paves the way of all modern deep learning practice, theory, and algorithmic design. Okay, and I'm going to show you later in a few lectures, what steps people take, to get from this very foundational model to all the modern practices. Some are correct, some are questionable, and you can form your judgment about which one you like to practice. So a Boltzmann machine is defined by an undirected graph model like this. It's a binary graph. Okay, very, very simple graph. And in this graph, there are two types of nodes. One are the visible units. They are actually something that you can view from data. For example, these are the pixels, okay, values from an image. Okay? And then these nodes are made to be hidden variables or hidden units. So they are not seen by people. They are something you need to compute or estimate. And we're going to talk about inference algorithms in later lectures as well. So what they correspond to, they may correspond to latent representations, features. They may correspond to class labels of your image. Anything that you imagine are sitting behind the semantics of the image, but you don't know, you want to derive from data. So these are the placeholders for those stuff. Okay? But the beauty of the graphic model is that once you have a placeholder, you can imagine you are the God. You can manufacture the whole world by building relationships. You can imagine that, the way I view a blue, a pixel here is because this guy indicates a sky. Therefore, I'm going to build a connection in here. You can literally build that, okay, from a top-down first principle approach, and then you will throw them into the real world and say, what's the parameter here? Right? You basically just place a placeholder for relationships to be honored, and then how the relationship, what's the strengths, you can learn them from data. Okay, so that leads you to a very, very simple model, literally following our Hammerstein-Clifford theorem kind of guideline. You are going to introduce what is known as the pairwise potentials, right, which are here. And you have these many pairs. They are bipartite graph. Therefore, only the pairs between two layers are present. And then you can introduce singleton potentials or singleton energies. Okay, and they give you some intuitive kind of intrinsic properties of every single unit. For example, on a particular location in the image, you may say that the likelihood, the tendency of seeing blue versus seeing red versus seeing green is 5 for 1, something like that. Okay, so that's a singleton potential, right? And also in the hidden part, you also have the singleton potential. You can say that the labels, sky and the land and water, for example, may have a three-way even breakdown. 3.33, 1 over 3 versus 1 over 3, and so on and so forth. Or maybe there's a bias. So you can design that. Or you can just put a placeholder there and learn it from data. Okay? So that's basically the model. These weights are interesting because they are unknown numbers. You can also specify it, but you can also make it to be an unknown number. Then you plug in the real data, and I'm going to tell you later on how to train it, estimate this data from data. Again, for any famous model, people compete for credits, right? So not surprisingly, there are multiple names, for this model. We know a name called RBM. Smolinsky, actually used this very same architect for his model, and it's called harmonic. So probably don't know that word is. It's a little instrument in the ancient world, which looks like this. Maybe a small harp, something like that. Okay. And then, in fact, I provide a little history here for your entertainment. You can read it. And the RBM actually has some very important mathematical properties that I want to start flash at you so that you can appreciate why people prefer a graph like this versus many other things when they want to get real work done. First of all, when you are removing all the hidden random variables, not hidden variables, but any random variables from the other part height, like this. Sorry. Okay. You can actually prove to yourself that we're going to prove that later, or maybe you don't need to prove after we learn more. These random variables, without the other part present, become dependent of each other. They are literally all dependent. Therefore, what does it say? It kind of says you something intuitive in natural world. It means that if you don't see evidence in real world, your brain is a mess. Your brain has all the concepts convoluted and connected. At least statistically, in building a model, if you don't have any real data as the input, you just purely want to model a set of random variables that is hidden as a concept, you should assume that they are all interdependent. Okay? Kind of a natural philosophical statement, but it is true. But RBM has the nice property, due to our Markov independence, structures and so forth, which allows you to establish the following. If this part is present, you can actually prove that given the observed, the orange layer, every pair of green nodes become conditionally independent. Okay? So that's a very, very nice property, which means that this guy, let's call this H, let's call this V, okay? And this P of H, which is the set of all hidden random variables, given the observation. Oh, okay, I already have a name for that. This is H, this is called X. Good. Okay. I should rewrite this. So P of H given X become a product of P of HI given X. Okay. So that's very important. You can now literally factor, the whole joint of hidden random variables or any set of random variables on this part to be a product of a singleton. Okay. And likewise, you can do the same for of P of X given H. They all become independent. Okay. So RBM allows this kind of factorization, okay, which actually makes a lot of the calculation and the sampling easier when you are going toward the calculational part or the inference part. Because you can imagine writing, defining, or drawing samples from a univariate distribution is way more easier than coming from a big joint distribution of many things, right? And also writing down this little thing is also very easy. You can imagine just a simple regression function from all this to here using a linear dependence or other things. So design component becomes easier. And that was the original kind of incentive. Sorry. And it enables what the algorithm called the iterative gap sampling, which we are going to run into in the future. But the idea about this iterative gap sampling exactly comes from the conditional independence properties, okay, which allows you to save some work. Yeah. So in a sense, people ask you, why care about conditional independences? We never use it in neural network or in other fancier work now. Well, they become so invisible in terms of their value because they guarantee you to take simple steps in computation without losing correctness. Okay. And there also, exist some fancier learning algorithms that allows you to get those estimators. So let's use what I just discussed to come up with a constructive definition of the RBM model. So as I said, we have the hidden layer, we have the visible layer, and the hidden layer now can basically be factored into a product of a singleton conditional distributions. Okay. Therefore, all I want to define is basically a G function or a potential function on that particular singleton. Okay. And likewise, you can define singleton potential functions for the visible layer. And now, of course, you need to have a coupling terms which allow both x and y to be defined. And then we do very simple. We just multiply these two together because you already define singleton, and we can just multiply them. That's one way of defining that. You can define others, but this allows simplicity. So this is a constructed definition of the RBM model. And then what this is trying to say. What this is trying to say is that yeah, this is a little bit tricky, but I can say a few words about that. Whenever you define, say a singleton, for example, P of H, okay, or P of X, you usually pick a very, very intuitive distribution. Say maybe this is a Gaussian distribution, and therefore it is a n of H given mu and sigma, for example. Or maybe this is a multinomial, therefore it is a multinomial of, in fact, I use, x, given some frequency of the events, something like that, right? So that's basically how you define a marginal distribution for a particular random variable. What this actually, if bunch of equations is showing is that because of this conditional independencies, you are now able to write down the joint distribution of this hidden random variable or the set of observed random variable as a product of a singleton conditioning on the rest of the layer as the evidence. Okay? In a sense, you are getting closer to just using this as the definition of the singleton distribution in the model, not in isolation, okay, but given some evidence. And what's the impact of those evidence? These equations are trying to say that the impact of those evidence is just to shift these original parameters with some values. They just bias the number to some other numbers. Okay. So that's basically the virtue of the graph model. Now, even though you have a big graphical model of many nodes, you can start from a very, very localistic and experience-based design for simple models, like a one-dimensional Gaussian random variable or one-dimensional multinomial random variable, and make these manipulations of shifting the value where the shifts are computed from the inputs of the data, and get a model like this, just by combining and multiplying them together, and get a complex model. Okay. So this is your first kind of run into the more complex model construction. We're going to go through that later a little bit more, but I'm going to stop here and so that we can see a few more such instances, and then later on we're going to dive into it more carefully, especially when we talk about graphical neural network models. I have a few more examples where I even put the context into the model, where I call this the text, call this the word, or topic, call this the word, how to model that explicitly using known models. But again, we can skip that for now. Another model I want to have a few words is another famous model known as the conditional random fields. Why I need to say a few words. First of all, it is a model invented here in CMU a long time ago by Professor John Lafferty. It was one of the fundamental kind of a building block now for many of the natural language processing tools. And also the image model that you saw before, using the easy model was actually an instance of this in the two-dimensional space. But here is the CRF model. It is a model basically over a sequence of random variables. Okay? And imagine this sequence of random variables are what? Say, part of speech tags in a particular sentence, nouns, verbs, and other things. And they want to be dependent, right? And this model basically offers a very simple way of modeling the dependencies given the entire sentence. Okay. It is built on features like this, which are pairwise. And sometimes people will add also the singleton features of xi. And why this is very interesting, because these building blocks allow the user to inject a lot of domain knowledges. Such as in here. Okay. For example, here I can literally, what is this about? Yeah, this is an irrelevant page. You will be needing it when we see the next, direct graph model lecture. So let's pass that. So here is a blow up of the configuration, the specification of the CRF model. And you see there are two types of components. One is called the edge potential, and the other is called the node potential. Same way as we see before, But in here, the CRF is built on what is called the CRF, conditional random field. We have the random field in the past. Your graphic model is called random field, but we are not giving evidence into the graph, conditioning on X, which is a full sentence, or maybe even more, such as a whole page of text. So why that is interesting? Because if you want to model a long and large entity, you need to build a big contingency table for all the random variables in that, right? Which makes the cost of modeling very expensive if you want to write a single function for that. And then our trick is to build these local functions only on edge and nodes. But if the edge and nodes are built such that they ignore the global context, they can be sometimes not very informative. For example, in a sentence, whether this particular pair of words appeared at the beginning of the paragraph, or at the beginning, or maybe whether it is a bold-faced or italic, all these other features can be also very interesting in determining whether it is a particular, it carries a particular semantics. So these kind of properties is based on larger evidence, not just the local information. Right? So by conditioning on X in here, you have the opportunity to build in large evidences from the total data into the formation of the local features. Maybe taking the graph as example in here, for example, if I condition this node and that or this particular feature with the whole kind of image information, say this part is on the top of the image, or this whole image is about recreational and resort and so forth, then the way I build features connecting two neighboring areas may be different if I'm modeling the whole thing in a desert. Right? So very vague, but it gives people a lot of flexibilities in incorporating long range and global evidences. So here are some specific explanations of what those little symbols mean in terms of their semantic and statistical meaning. But at the end of the day, you basically use the Hammerschlag-Clifford theorem to combine them together: edge potential, single potential, and partition function. These are the three components inside a conditional random field, and then you can use it to model many sequential and high-dimensional data. In this case for language, and in this case for image. So that's our second model of instances of the undirected graph model. We're going to talk about how to learn these parameters and how to infer all these hidden nodes, given the data in our later lecture. So stay tuned. So just to sum up, So today, I want you to go home and have this take-home message. One great class of graphic models is known as the undirected graph model. And they actually encodes a whole bunch of conditional independencies. And today we'll talk about the global, local, and the pairwise. Remember that. And then there is a correspondence between a graph entity and a probabilistic distribution. Okay, and the bridge of this correspondence is called the IMAP. Okay, so that independencies from one set can be honored or reflected in the other set, and therefore you can choose to work on the simpler side that you prefer, without losing all the powers and the capabilities of the entire space. And remember, you want to capture these names, potentials, cliques, correlations, and so forth. In the future, it will be very useful, especially this Markov blanket concept. Now, can you still recognize the Markov blanket in this graph? It's a little bit more irregular than the other one. The green one are the Markov blanket of the yellow one. And it will make your life extremely easy. So I want to conclude with just one equation in the future you can use to save your time. Under the Markov blanket independence or the local Markov dependencies, when you want to define a distribution of x, given x minus I, the entire universe of the random variables, minus the variable of interest, which is our typical way of writing non-conditional distributions. Okay. In fact, if you go through an algorithm called Gibbs sampling, it always asks you to sample a random variable given all the rest, which can be extremely difficult. With this, you can write them down as a P of xi given P of a Markov blanket of I, which is a matter of conditioning on 3 random variables instead of another 10 random variables. Okay. So this property will be used very often in the future for many of our learning and inference protocols. And so I want to stop here. In the later part, there is an appendix for you to take a look at how people usually learn the structure from data in the simplest case. We may be touching upon that later on when we have time to talk about the causal inferences.